Your laptop is not broken. It is doing exactly what it was engineered to do. And that is the problem. Beneath that aluminum chassis, a war is being fought between hardware built for one era and software demanding the resources of another. The CPU is not failing. It is throttling itself, pulling back its own clock speed just to keep from melting through its own casing. That is called thermal throttling, and it is a mechanical reality baked into the silicon. What you feel as sluggishness is actually a machine protecting itself from demands it was never designed to meet. This video is brought to you by the Durability Project, where we explore why the things we buy no longer last and the engineering decisions that quietly shape their lifespan. Imagine a locomotive engineer, mid-run, who looks ahead and realizes the track was built for a single car. He is pulling 100. The machine isn't slowing down randomly. It's exceeding the limits it was designed to operate within. RAM is not storage. People confuse the two constantly, but they are completely different animals. Storage is the warehouse, the hard drive or SSD where your files sit when nothing is happening. RAM is the workbench. It is the live, active surface where every running process does its work. When your machine opens an application, that application climbs onto the bench. When it needs to calculate, render, or respond, it works right there, on that surface, and that surface has a fixed size. A machine sold with 8 gigabytes of RAM sounds like enough room to work. It sounds generous even. But modern Windows or Mac OS does not wait for you to open anything before it starts claiming that space. The operating system itself, its kernel, its drivers, its background services, all the structural bones that hold the software skeleton upright, consumes somewhere between 3 and 4 gigabytes just sitting at the login screen. Half the workbench is already covered, and you have not touched the machine yet. The problem isn't that you ran out of memory. It's that you never really had as much as you thought. When RAM fills, the system spills over into virtual memory, using your drive as a substitute. And even the fastest SSD is not RAM. It's a fallback, and every time the system uses it, you feel the cost. Browsers make this worse in a specific and severe way. Each open tab is not a passive page sitting in memory. It is a live process, running scripts, preloading content, syncing with servers. A single tab can consume 200 to 400 megabytes of RAM on its own. So 10 open tabs is not 10 pages. It is 10 engines running simultaneously on a workbench built for 3. Chrome, Edge, Firefox. They all operate this way because the modern web demands it. A tab isn't a page, it's a process. And then there are the background sync applications, cloud storage clients, email clients, calendar apps. These are designed to run invisibly and continuously. They are not malicious. They are doing exactly what they were built to do. Keep your data current. Keep your files backed up. Keep your calendar accurate. But their draw on RAM and CPU cycles is constant, invisible, and cumulative. You never see them. You only feel the weight they add. The machine you saw on the showroom floor was fast because it carried none of this. A clean, freshly imaged device with no user data, no cloud sync, no open tabs. That machine is a different beast entirely. The machine you actually live on is loaded. And when the workbench hits its ceiling, every new request waits in line behind every other request that got there first. You press the power button, the desktop appears. It looks quiet, looks ready, looks like it is waiting on you. But inside that chassis, dozens of processes have already clocked in for a shift you never authorized. They are drawing from the same CPU, the same thermal budget, the same finite pool of resources you expect to be yours when you open your first application. Startup programs are the most visible part of this. Every application that installs itself into the startup sequence, a printer utility, a music player, a video conferencing client, adds its own initialization load to the boot process. They all compete for CPU cycles and RAM during the exact window when the system is already under maximum strain. The machine is not even fully awake yet, and it is already being pulled in a dozen directions at once. But startup programs are only the surface layer. Beneath them runs something deeper. Operating system background services that are not optional, not user-installed, and not visible in any standard task manager view without deliberate investigation. Windows Update orchestration, telemetry reporting, indexing services, security scanning. These are structural components of the OS. They run on a schedule the user does not set and cannot easily override. They came with the machine the same way load-bearing walls come with a building. You did not choose them. They were already there. Think of it like a factory floor. The machines you bought are running, right? But so are dozens of maintenance crews, inspectors, and supply chain workers you never hired, all drawing from the same power grid, all generating heat, all competing for floor space. You didn't hire them. They came with the building, and every watt they consume is a watt your production line does not get. Windows Defender alone, the built-in security tool, the one running on virtually every Windows machine by default, runs scheduled full system scans that can peg CPU utilization at sustained high levels for minutes at a time. And these scans do not always fire during true idle periods. They fire during what looks like an idle period, which often coincides exactly with the moment you open something demanding. The CPU was already committed. You just did not know it. This is where thermal throttling enters the picture, and it enters as a direct consequence of everything above. A CPU under sustained high load generates heat. Real, physical heat, building inside a chassis the size of a hardcover book. And modern laptop CPUs are engineered to protect themselves by reducing their own clock speed when internal temperatures cross a threshold. This is not a malfunction. It is a survival mechanism written into the chip's own microcode, the machine pulling back its own power to keep its silicon intact. Thermal throttling isn't failure, it's self-preservation. The cooling system inside a thin laptop chassis, a heat pipe, a small fan, sometimes a vapor chamber in the premium models, has a finite capacity to move heat away from the processor. When background processes push the CPU into sustained load, that thermal budget is spent before your application ever gets its turn at the bench. So you open a video editing timeline or a large spreadsheet, and the machine feels like it is wading through concrete. Not because the CPU is weak, but because that CPU has been running hot for 10 minutes, has already pulled its own clock speed down to protect itself, and is now being asked to sprint. The chassis is not armor. It is a constraint, and inside that constraint, the machine is quietly, constantly, and deliberately pulling back its own power just to survive. The machine is not broken. It never was. It is a precision instrument running inside a set of constraints it was built with from day one. Thermal limits, memory ceilings, background obligations baked into the silicon and the software both. The gap between what it was dimensioned to carry and what modern software now demands is not a defect. It is just the mechanical reality of an industry where software appetite outgrows silicon on a yearly basis. Knowing that gap exists is what turns a frustrated user into someone who actually operates the machine correctly, closing background processes, managing startup load, respecting the thermal envelope. That is not a workaround. That is stewardship. If the software keeps growing and the hardware keeps shrinking, something has to give. Right now, it's performance. The question is whether that trade was ever made for you. Brought to you by the Durability Project.